Section 5.9. Solving a polyalphabetic cipher. Once you have found the period using either the Kasiski method or the index of coincidence, the next step is to solve the individual alphabets. Let's look at the easiest case first, the Balazzo cipher. Section 5.9.1. Solving a Balazzo cipher. With the Balazzo cipher, all of the substitution alphabets are simply the standard alphabet shifted by some amount. Determine the amount and you have solved the cipher. The first step is to separate the characters that have been enciphered with each letter of the key. Let's look again at the example from section 5.5. Since we have determined that the period is 6, let's write the cipher text in groups of 6. The first letter in each of these groups has been enciphered with the first letter of the key, the second letter in each group by the second letter of the key, and so forth. If we wrote the cipher text vertically in 6 columns like this, then the first column of letters would be enciphered with the first letter of the key, the second column of letters would be enciphered with the second key letter, and so on. Consider each letter column separately. Each column will have the normal English letter frequencies, but shifted according to its key letter. If we can determine the shifts, then we have solved the cipher. I will describe 2 methods, one for hand solution and one for computer solution. Let's look at the paper and pencil method first. For each column, we can make a frequency count. That will give us 26 numbers. For paper and pencil solving, it is better to display the frequencies as a histogram, bar graph. The histogram for the first column of the cipher text would be. With only 18 letters, this is rather sparse, but it is enough. Let's compare this to a histogram of standard English letter frequencies shown next, and try to figure out the shift. Some of the visual characteristics of this frequency distribution are 1. E is by far the tallest peak. 2. There are 3 peaks evenly spaced 4 columns apart, namely A, E, I, where I has the companion H. 3. There is a double peak at N, O. And 4. There is a triple peak at R, S, T. Let's try to match this histogram to the ciphertext histogram. We start by looking for a tall peak that could represent E. There are 2 tall peaks, R and Y, corresponding to key letters N and U. That is, if E is enciphered by N, the result is R, and if E is enciphered by U, the result is Y. Next, let's look for 3 peaks 4 spaces apart. There are 2 candidates, G, K, O, and N, R, V, corresponding to key letters G and N. How about a double peak? Likely candidates are N, O, and Y, Z, corresponding to key letters A and L. What about a triple peak? There is only one choice, the triple peak at X, Y, Z. This corresponds to the letter G. The most likely key for the first column is G, which produces the A, E, I peaks and the R, S, T triple peak. The second most likely key is N, which gives E as the most frequent letter, and the N, O double peak. Let's turn our attention to the second column of the ciphertext. The letter frequency histogram is. This time the ciphertext letter S catches our attention. If S represents plain text E, then the key must be O. Let's check this out by comparing the ciphertext histogram against the shifted alphabet. You can see that all of the high-frequency letters in the ciphertext, namely C, G, H and S, correspond to high-frequency plain text letters, namely O, S, T and E respectively. This is an excellent fit, and the second key letter is very probably O. The keyword starts Go. The other 4 key letters are determined in the same way. The keyword is govern. and the plain text is, "The legislature shall be divided into two chambers, the upper called the Senate, and the lower is the House of Representatives." That is the hand method. Make the frequency distribution visual by using histograms, and then match the distributions by eye. For computer solution, we need a numerical method for eyeballing the distributions to find a match. The standard method found in every book that discusses polyalphabetic ciphers is to use the correlation coefficient, specifically the Pearson product moment correlation coefficient, named for Carl Pearson, a founder of modern statistics. If you know statistics, this will be familiar to you. You no doubt already have a statistics package with this function ready-made. Use it in good health. For everyone else, I will show you a method that is both simpler and faster, and exactly as accurate. When we match up two frequency distributions by eye, we are trying to match the tallest peaks in one histogram with the tallest peaks in the other histogram. If we multiply their heights, we are trying to get the biggest product. If you go down the alphabet and add the 26 products, then the sum will be highest when the tall peaks line up with one another, and lowest when the highest peaks line up with the lowest valleys. That's the idea. Try each of the 26 possible shifts, line up the letter frequencies of the cipher text with the shifted frequencies for standard English, and add up the 26 products. The highest sum will indicate the most likely shift. This tells you the most likely key letter. The second highest sum is the second most likely shift, and so forth. I call this technique the tall peaks method. The Belasso cipher is rated 2. Section 5.9.2. Solving a Vigenère cipher. About 30 years after Belasso, Blaise de Vigenère made two improvements over the Belasso cipher. The first was to add guides along the outside of the tableau. This had the effect of producing a mixed alphabet without the work of mixing the tableau. Here is an example using the key phrase "first love" in the horizontal guides and the keyword "youth" in the vertical guides. You will find the second improvement, AutoKey, in section 5.10. To encipher the letter B using the key letter U, find the key letter U in the key guide to the left or right of the row, and the plain text letter B in the letter guide at the top or bottom of the column. The ciphertext letter is the letter in the U row and B column, namely M. To decipher, use the key letter to find the row, find the ciphertext letter on that row, and take the plain text from the letter guide at the top or bottom. If you are enciphering by hand, I suggest drawing horizontal and vertical rules every 4 or 5 rows and columns, or use a clear plastic L square to find the intersections accurately. Here is a sample message enciphered using this form of Vigenère cipher. It has a period of 5. This cipher has a serious weakness. Since each row in the tableau is the standard alphabet shifted by a number of positions, each cipher alphabet will be the same as all of the other cipher alphabets shifted by some number of positions. You cannot usefully compare the cipher alphabets to the standard alphabet because they are in mixed order. However, you can determine the shifts by comparing the cipher alphabets to one another, either by eye or by using the tall peaks method. The following figure shows the histograms of the 5 cipher alphabets, shifted to match up their peaks and valleys. All of the ciphertext letters in the first column, shaded, represent the same plain text letter. This means S in the first alphabet, C in the second alphabet, and L in the fourth alphabet all represent the same letter. Replace all of these by A. There are no letters in the second column. In the third column, M in the third alphabet and T in the fifth alphabet represent the same plain text letter. Replace all of these by C, and so forth. The ciphertext letters in the 26th column would all be replaced by Z. This converts the ciphertext into a simple substitution, which can now be solved using the methods of section 5.1. The Vigenère cipher is rated 2.